Okay, what I wanted to talk about were some of the impact craters that have been formed by the Ranger spacecraft and the Saturn S4B booster stage. There are similar craters that presumably were formed by the Ascent stage of the Lunar Module, but we haven't found those yet. So this just shows Ranger, the S4B, this was before the LEM was extracted, and the upper stage of the Lunar Module, which were all crashed into the moon. And the advantage of looking at the craters from these is they're fairly well understood. We know where they are, we know the mass of the vehicle, we know the speed of the vehicle, and we have a pretty good idea of what the impact geometry was, and so that can provide us with some understanding of the crater. Now, most of the craters on the moon are formed by asteroidal material or cometary material coming in at very high velocities, anywhere between 10 and 40 kilometers per second, and the densities range from 1 if it's cometary up to 7 if it's iron. And so these things come in with a lot of kinetic energy and produce the conventional craters that you see. For these vehicles, mostly what we're talking about is a tin can that's coming in at a very low velocity. And the most important thing is that the bulk density are very, very low. They're typically on the order of 0.02 or 0.03 grams per cc, as opposed to 3 or 4 if it were a rock. A lot of the energy gets consumed in crushing the vehicle, and so there's that much less that goes into the excavation of the crater. And finally, the question is what happened with LCROSS, because LCROSS impacted the Centaur stage, and it similarly had a very low bulk density and came in at a relatively low speed. So Ranger is about 3 meters tall. It's about 1.5 meters across here and about 4.5 meters across the solar panels. As I said before, a very low bulk density and coming in at a very low velocity on the order of 2.6 kilometers per second. The craters that have been recognized are on the order of 13 or 14 meters in diameter, and I'll just go through some set of pictures. So this is the crater. They have very prominent ejecta patterns, and when you look at them from at high sun, in this case the floor is relatively flat, and it hit the Mare surface. Ranger 7 similarly hit a Mare surface, and at low sun they look like any other impact crater. At high sun is when you can see the interior morphology and the very prominent ejecta blankets. Similarly, Ranger 8 hit a Mare surface. You can see the dark and bright ejecta coming away from the crater, and a little bit of the interior down here. And finally, Ranger 9 hit the floor of Alphonse's crater. So this is a different material, impact melt or something else than just simple Mare basalt. It looks a little different. It's got a little more prominent ejecta blanket. What typically occurs in these craters is the floor is relatively flat or has a somewhat concentric morphology, similar to concentric craters that you see small diameters on the regolith. Just to give you a perspective, the red arrow indicates the direction the spacecraft was going when it impacted. The number, if you can see it, indicates the angle from vertical. So these two are fairly steep, these two are fairly shallow, but you can see that more or less the asymmetries that are associated with the ejecta blanket are consistent with relatively little material going back uprange and stuff going downrange, but a lot of material going off sort of perpendicular to the velocity vector. Okay, the Saturn V S4B was the third stage up here. It was about 17 meters long and 6 meters in diameter. And again, when you look at the bulk density of the vehicle after the fuel was expended, it has a bulk density of 0.02-ish grams per centimeter cubed, so very low density. This is what it looks like. This was one of the early Apollo missions that was testing it before they put the Lunar Module in. This is also just an Earth orbiting mission, but you can see the Lunar Module here, which was extracted, and in this part was sent onto the moon to intentionally impact the surface. These craters are obviously, it's a bigger vehicle. The velocities are similar, 2.5, 2.6 kilometers per second. The craters are a little bit larger. They're on the order of 35-ish meters in diameter, but they're all asymmetric. The Ranger craters were pretty much circular. These are all a little more asymmetric, but not by much, a few meters longer in one dimension than the other. As I said, we haven't found the Apollo 16 crater yet, so we don't have a dimension for it. This is a typical high sun picture, and you can see the extensive ray system coming out. And this is a regional context that landed on the edge of this crater here. Up close, again at high sun, you can see the nice thin ejecta pattern coming out. And then when you look at it at low sun, the thing that's peculiar about the S4B craters is they all have this mound in the middle here, which is on the order of 15 or 20 meters long and a similar amount, although it's narrower this way. And this occurs in all the S4B crater. This is what Apollo 14 looks like. This one also landed on the Mare. Again, this one's a little less well developed, but it still has this sort of north-south trending ridge in the middle. Apollo 15 also hit the Mare surface. High sun, again, you can see the prominent skinny rays coming out and the central mound here. And finally, Apollo 17, similar, extensive rays extending out for kilometers on a Mare surface. And the interior, this one doesn't have as well developed the central mound that's a little more oblong, and it seems to be connected to the southern rim here. But the characteristic is the same pretty much in all these craters. And when you look at the direction and the impact angle, these two were fairly steep. You get a pretty much symmetric ejecta blanket. And then when you get down a little farther, Apollo 17 was the most asymmetric, and the ejecta pattern is a little more asymmetric. Okay, we haven't found the Ascent stage craters yet. It's not clear why. The only difference is these came in at a very low impact angle, a few degrees above horizontal, and so maybe they have a different morphology. This just sort of illustrates that the S4Bs and Rangers all came in fairly steeply. The Lunar Module Ascent stage came in at a very low angle. And so maybe the morphology of the crater is different. But to sort of make a comparison between the two, the Ranger craters are about 14 meters in diameter. They both Ranger and S4B have very extensive long bright ejecta rays, both bright and dark material. They're both shallow. This one, the Ranger craters typically have a flat floor, and in some cases it looks like there's a concentric morphology with a little ridge just at the bottom of the crater wall. The S4B craters have this elongate ridge in the center. There are very few boulders associated with any of these craters. There are a couple associated with some of the S4B impacts, and the question is whether those really are boulders associated with that were ejected from the impact, or whether they are just boulders in the area that happen to be nearby where the crater formed. The Ranger craters are pretty much circular, whereas the S4B craters are not. One can think about the target properties, and these craters are all fairly small. They're only tens of meters in diameter, and they're only a few meters deep. And so most of them hit the Mare surface. And so the target properties are a layer of basalt. This is looking across Hadley Rill with a layer of regolith on top. And there's a whole series of studies that go back to the Quaid and Overbeck era that came up with schemes like this, where the thickness of the regolith over the basalt was an important parameter in the morphology of the crater. And depending upon how big the crater was with respect to the regolith thickness, you got different morphologies. The other thing to think about is if we're just making craters in the regolith, we need to think about the density of the target material, which is not 3 or 4. It would be for a solid rock. It's around 1.7 or 8 for the regolith. And this just shows some typical Mare craters where you can see a variety of odd interior morphologies that are reflecting variations in the regolith thickness and the impact process. This was alluded to this morning, some stuff that Pete Schultz and his students have been doing, where they looked at the ejecta for low density impactors into material. This may influence how the crater rays are formed. Some of the ejecta patterns look a little different from typical impact craters. It's not clear that this really influences the morphology, though, although the fact that we have this mound in the center of the S4B craters suggests that there's something odd about making impact craters with long, skinny, low-density projectiles. The other point that's important here is that these particular impacts, the S4Bs and ultimately the Lunar Module Ascent stages, were used for the seismic calibration. And so at least now we can put them all in the same coordinate system. The locations are, in some cases, considerably different from what was estimated during the Apollo era. So now we have a uniform coordinate for both the individual impacts as well as the seismometers at the Apollo site, and so that may or may not change some of the velocity models that people have looked at. So, in conclusion, we're talking about low-density, low-velocity projectiles. They produce very extended ray systems with both bright and dark material. They're all, except for Ranger 9, the ones we've seen so far, all landed in Mare material. It would be nice to see one in the Highlands, which would be more applicable to the LCROSS impact, which hit into presumably mega regolith. There's a concentric mound in the S4B craters. There's a concentric sort of ridge for the Ranger craters. I think the regolith influences the crater morphology to a considerable degree because the craters are small and the regolith is relatively thick. If you take the standard cratering equations and use a low-density projectile for the energy that these events had, you can calculate a diameter that matches pretty well with the observed diameter. So there's nothing particularly odd, but it does serve to provide a constraint that impacts that we're observing on the moon are consistent with the sort of theoretical and experimental work. Thanks.
We have time for questions.
Going to ask a question or make a speech? No.
Do you have any opinion on whether or not there would be any recognizable pieces of the impactor in any of these craters?
I think so. The talk this morning showed that you know in the experiments in the vertical gun you can pick out little pieces of the projectile that survive the impact. I would think there would be pieces laying around. Now I think the mini RF guys, Spudis and Bussey, have looked at some of the sites but didn't see anything obvious. So maybe they're there, maybe they're buried. Somebody at one point suggested that the mound in the S4B craters was the debris from the vehicle, but there's a lot more volume of material there than there. But there could be scraps of metal laying around.
Yes.
Do you think the LCROSS impact then was more S4B-like or more Ranger-like? What's your guess?
I think it's closer to the S4B than it is to Ranger because it's a similar vehicle. The S4B was a larger event, but I think it excavated a shallow depth. There may be something funny about the interior morphology like we see at the S4B. That's why it would have been nice to get one of these into true highlands. It would be a better analog for LCROSS.
Any other questions?